Hello and welcome to the Certified Kubernetes Administrators course. My name is Mumshad Manambat and I will be your instructor for this course. So about me, I'm a solutions architect. I specialize on cloud automation and DevOps technologies. More on this coming soon. We also have a dedicated Slack channel that you get exclusive access to, where experts and other students gather to help you clear your doubts and get instant support on your queries. We will also discuss some tips and tricks throughout this course to help you crack the certification exam. And as always, if you have any questions, you may reach out directly to us through our Q&A section or the Slack channel. Now, this is one of the courses in the series on Kubernetes and focuses on getting the Kubernetes Administrator certification. So having a basic understanding to some of the concepts and prerequisites will help. Knowing basics of Docker and some basics of Kubernetes itself, such as pods, deployments, and services, and having a good understanding of the YAML language, setting up a basic lab environment using VirtualBox can all help in this journey. We do discuss setting up a Kubernetes cluster in detail in this course, and we also have online labs and practice tests for a lot of these concepts. But if you're an absolute beginner, I highly recommend taking the Kubernetes for the Absolute Beginners course first, which is a short, quick introduction to some of the basic concepts. Let us now look at the course objectives. The objectives of this course are aligned to match the Certified Kubernetes Administrators exam curriculum. We will discuss about details around the certification itself in one of the upcoming lectures before heading into any of these topics. However, remember, this is not just a course to clear the certification. We discuss a number of other related topics, and the intent of this course is to get you to be good at installing, configuring, and troubleshooting a Kubernetes cluster. With the way the contents are organized in this course, we do not start the course by building a cluster from scratch. We actually do that towards the end of the course in the installation, configuration, and validation section. You will be working on pre-built live clusters throughout the earlier sections in this course, and I think that makes sense. Think of this as learning to engineer and build a car. It would be much easier if you have already driven a car, know how it works, what the wheels are for, what the transmission is for, what the brakes are for, and how to fill fuel, etc. That way, you would be able to relate those to the underlying concepts better when you learn them. And that is why I think practicing on pre-built clusters and learning the basic concepts first will help you understand how to build a cluster from scratch towards the end of this course. We start with the core concepts, where we look at the various components that form the Kubernetes architecture. We then discuss some of the API primitives. Here, we mostly recap what we learned in the beginner's course about pods, replica sets, deployments, namespaces, etc. We then look at services and other network primitives. In the next section, we look at scheduling. We start with labels and selectors, followed by daemon sets and how resource limits can affect pod placements. We look at ways of manually scheduling a pod and configuring multiple schedulers and how to view the scheduler events. In the logging and monitoring section, we look at different ways of monitoring and logging the cluster components, as well as applications hosted on the cluster. In the application lifecycle management section, we look at rolling updates and rollbacks, and various ways of configuring applications, scaling applications, and the primitives necessary to create a self-healing application. In the cluster maintenance section, we look at the different options available to take down a node in the cluster for maintenance purposes. We then look at how software releases are organized in Kubernetes, followed by the cluster upgrade process. You will perform an upgrade to a live cluster yourself in the practice test without taking down the application. And finally, we look at the different backup and restore methodologies. We then move to security. We start by looking at different ways of authenticating into the Kubernetes cluster. We take a good look at TLS certificates. We start all the way from the absolute basics of TLS certificates into how exactly a cluster can be secured with these. So there are many practice exercises around that. You will be asked to troubleshoot and fix issues related to certificates, which I believe will give you confidence in working with certificates. We look at the new certificates API. We then look at role-based access controls and attribute-based access controls for authorization. We then look at network policies and security contexts. In the networking section, we start with some optional networking prerequisite lectures. This will help you understand and troubleshoot networking in Kubernetes in depth. So we start by understanding the basics of networking in Linux, basics of switching and routing, and birth networks in a Linux system. We try and understand the basics of DNS, what core DNS is. We then look at network namespaces and then relate those concepts to networking in Docker. We then start with networking in a Kubernetes cluster. We look at CNI and what they are. We look at one of the CNI networks in depth and how it functions. We look at how service networking works under the hoods. We then look at DNS in Kubernetes cluster. And finally, ingress networking. And of course, this section is filled with practice exercises where you will practice viewing and gathering network information from a cluster, implementing network configurations, and troubleshooting network-related issues in a cluster. We then look at designing, installing, configuring, and validating a Kubernetes cluster from scratch. We use Kelsey Hightower's Kubernetes the hard way as the basis for this, but we deploy the cluster on our local machine using VirtualBox and Vagrant. We understand how a high availability cluster works and how an etcd cluster works and the best practices in deploying an HA cluster. We look at two ways of bootstrapping a worker node, one the usual way and the other using the TLS bootstrap approach. We finally perform end-to-end tests on the cluster we deployed using the Kubernetes testing infrastructure. With all of this, you should have gained enough knowledge on how the various components work together in a Kubernetes cluster. So troubleshooting piece should come to you naturally. We look at some techniques that can be followed while troubleshooting a cluster and applications running on them. Again, we have a number of practice tests where we give you a broken cluster and you troubleshoot and fix them. Well, that's a lot, and we plan to add more relevant topics to this list going forward. Finally, a word about practice tests. The Kubernetes certification exam is a practical hands-on exam, so it is very important to practice what you learn, which is why we have built a custom solution that will give you access to a real Kubernetes environment right in your browser, along with a quiz portal that provides fun and challenging problems for you to solve. You're required to gain a set of different skills working with Kubernetes, such as how to look for information, how to troubleshoot issues. That is why we have questions where you will be asked to find information within an environment. You will also be asked to perform configuration tasks where you will be required to configure and deploy applications and services on the cluster. We will test your work and provide feedback instantly. We will occasionally make changes to the environment or break stuff and ask you to troubleshoot and fix them. These are common issues that one would face while working with Kubernetes, and these exercises will help you troubleshoot and fix issues quickly. When you see an error message, you should be able to understand what that means and where to look for information related to that error message and how to fix it. One of the major challenges in a practical test like the one in the Kubernetes certification is time. Even simple issues like a typo or an indentation error in a YAML file can take a beginner hours to fix. This is why we have hundreds of such exercises in this course that will make you an expert and give you enough practice to help you clear the exam. Well, that's all for now. Thank you for enrolling, and I'll see you in class. Hello, and welcome to this lecture. In this lecture, we look at some of the details around the Certified Kubernetes Administrators program. What is it, why you need it, and how to prepare for it. There's no doubt about the fact that the adoption of Kubernetes is expected to grow exponentially in the coming years, as seen in the graph from Google Trends. As per a recent survey conducted by Indeed, Kubernetes had the fastest growth in job searches, over 173% from a year before. And so it is important for us to be prepared to establish credibility and value in the market. The Kubernetes Administrator certification, developed by Cloud Native Computing Foundation in collaboration with the Linux Foundation, does just that. It helps you stand out in the crowd and allows companies to quickly hire high-quality engineers like you. On attaining the certification, you will be certified to design, build, and administer highly available Kubernetes clusters. You can read more about the certification at cncf.io/certification/CKA. As of today, the exam costs $300 with one free retake. In case you don't manage to pass on the initial attempt, you have one more attempt available for free within the next 12 months. The mode of delivery is online. You can deliver the exam anytime, anywhere at the comfort of your house. Since this is an online exam, an online proctor will be watching you at all times. There are a set of requirements that need to be met with respect to the environment, the room you're attending the exam from, the system you're using to give the test, your network connectivity, etc. All of these are described in detail in the candidate handbook available on the certification website. Unlike most of the certification exams out there, the Kubernetes certification is not a multiple choice exam. It is an online, performance-based exam that tests your hands-on skills with the technology. This would mean that you don't have to worry about memorizing lots of different numbers in preparation for the exam. However, you need to know how the technology works and how you can get it to work. You will be given different tasks to complete in a set amount of time, which happens to be 3 hours for this exam, as per the exam guidelines. You will, however, be able to refer to the Kubernetes official documentation pages at all times during the exam. And in this course, we will walk through how to make best use of the documentation site so that you can easily locate the right information. Well, I wish you good luck in preparing for and delivering the Kubernetes certification exam, and I'm sure with enough practice, you will pass with flying colors. So let us begin. Hello there. Before we begin, I want to spend a minute on the Kubernetes series of courses. Kubernetes is one of the most trending technology in cloud computing as of today. It is supported on any cloud platform and supports hosting enhanced and complex applications on various kinds of architectures that make it a vast and complex technology. There are a set of prerequisite knowledge required, such as containers, applications, YAML files, etc. A lot of topics to discuss, a lot of concepts to cover, such as the architecture, networking, load balancing, a variety of monitoring tools, auto-scaling, configuration, security, storage, etc. There are students from different backgrounds, such as the absolute beginners to Kubernetes, or those with some experience looking for specialized knowledge in administration, or those from an application development background. And there are 2 certifications in the mix as well, one for the administrators and another for the application developers. Covering all of these topics for all of these students in a single course is an impossible task, which is why we created a 3-course series so each course can target specific audience, topics, and certifications. The Kubernetes for the Absolute Beginners course, the Certified Kubernetes Administrators course, and the Certified Kubernetes Application Developers course. Let's look at what we cover in each of these courses. The Kubernetes for the Absolute Beginners course helps a beginner having no prior experience with containers or container orchestration get started with the concepts of Kubernetes. As this is a beginner's course, we do not deep dive into technical details. Instead, we focus on a high-level overview of Kubernetes, setting up a simple lab environment to play with Kubernetes, learning the prerequisites required to understand and get started, understanding the various concepts to deploy an application, such as pods, replica sets, deployments, and services. This course is also suitable for a non-technical person trying to understand the basic concepts of Kubernetes, just enough to get involved in discussions around the technology. The Kubernetes for Administrators course focuses on advanced topics on Kubernetes and in-depth discussions into the various concepts around deploying a high availability cluster for production use case, understanding more about scheduling, monitoring, maintenance, security, storage, and troubleshooting. This course also helps you prepare for the Certified Kubernetes Administrator exam and get you verified as a Kubernetes administrator. The Kubernetes for Developers course is for application developers who are looking to learn how to design, build, and configure cloud-native applications. Now, you don't have to be an expert application developer for this course, and there's no real coding or application development involved in either this course or the certification itself. You only need to know the real basics of development on a platform like Python or Node.js. This course focuses on topics relevant for a developer such as config maps, secrets and service accounts, multi-container pods, readiness and liveness probes, logging and monitoring, jobs, services, and networking. This course also helps you prepare for the Certified Kubernetes Application Developer exam. All of these courses are filled with coding exercises and quizzes that will help you practice developing and deploying applications on Kubernetes. Now remember that there are some topics that overlap between these courses, so we recap and discuss them as and when required. Now you don't have to take these courses in order. If you're an administrator, you may choose to take the beginners as well as the second course and get yourself certified as a Kubernetes administrator, or take the beginners course and the developers course to get yourself certified as a Kubernetes application developer, which I'd say is the easier of the two if you were to ask me. So, if you're ready, let's get started. If you have attended the beginners course or other certification course for application developers, then you might want to skip some of these topics, or maybe just go through the practice tests alone. We will now start with the cluster architecture. If you have Hello and welcome to this lecture. We start with a basic overview of the Kubernetes cluster architecture. We first look at the architecture at a high level, and then we drill down into each of these components. We see what their roles and responsibilities are and how they are configured. And finally, you go through a practice test where you look at an existing cluster and are asked to identify various details with respect to these components in the cluster. We're going to use an analogy of ships to understand the architecture of Kubernetes. The purpose of Kubernetes is to host your applications in the form of containers in an automated fashion so that you can easily deploy as many instances of your application as required and easily enable communication between different services within your application. So there are many things involved that work together to make this possible. So let's take a 10,000 feet look at the Kubernetes architecture. We have two kinds of ships in this example. Cargo ships that does the actual work of carrying containers across the sea, and control ships that are responsible for monitoring and managing the cargo ships. The Kubernetes cluster consists of a set of nodes, which may be physical or virtual, on-premise or on cloud, that host applications in the form of containers. These relate to the cargo ships in this analogy. The worker nodes in the cluster are ships that can load containers. But somebody needs to load the containers on the ships. And not just load, plan how to load, identify the right ships, store information about the ships, monitor and track the location of containers on the ships, manage the whole loading process, etc. This is done by the control ships that host different offices and departments, monitoring equipments, communication equipments, cranes for moving containers between ships, etc. The control ships relate to the master node in the Kubernetes cluster. The master node is responsible for managing the Kubernetes cluster, storing information regarding the different nodes, planning which containers goes where, monitoring the nodes and containers on them, etc. The master node does all of these using a set of components together known as the control plane components. We will look at each of these components now. Now, there are many containers being loaded and unloaded from the ships on a daily basis. And so you need to maintain information about the different ships, what container is on which ship, and what time it was loaded, etc. All of these are stored in a highly available key value store known as IETCD. IETCD is a database that stores information in a key value format. We will look more into what IETCD cluster actually is, what data is stored in it, and how it stores the data in one of the upcoming lectures. When ships arrive, you load containers on them using cranes. The cranes identify the containers that need to be placed on ships. It identifies the right ship based on its size, its capacity, the number of containers already on the ship, and any other conditions such as the destination of the ship, the type of containers it is allowed to carry, etc. So those are schedulers in a Kubernetes cluster. A scheduler identifies the right node to place a container on based on the container's resource requirements, the worker node's capacity, or any other policies or constraints, such as taints and tolerations or node affinity rules that are on them. We will look at these in much more detail with examples and practice tests later in this course. We have a whole section on scheduling alone. There are different offices in the dock that are assigned to special tasks or departments. For example, the operations team takes care of ship handling, traffic control, etc. They deal with issues related to damages, the routes the different ships take, etc. The cargo team takes care of containers. When containers are damaged or destroyed, they make sure new containers are made available. You have the services office that takes care of the IT and communications between different ships. Similarly, in Kubernetes, we have controllers available that take care of different areas. The node controller takes care of nodes. They're responsible for onboarding new nodes to the cluster, handling situations where nodes become unavailable or gets destroyed. And the replication controller ensures that the desired number of containers are running at all times in a replication group. So we have seen different components like the different offices, the different ships, the data store, the cranes. But how do these communicate with each other? How does one office reach the other office, and who manages them all at a high level? The kube-api Server is the primary management component of Kubernetes. The kube-api Server is responsible for orchestrating all operations within the cluster. It exposes the Kubernetes API, which is used by external users to perform management operations on the cluster. as well as the various controllers to monitor the state of the cluster and make necessary changes as required, and by the worker nodes to communicate with the server. Now, we're working with containers here. Containers are everywhere, so we need everything to be container compatible. Our applications are in the form of containers. The different components that form the entire management system on the master node could be hosted in the form of containers. The DNS service networking solution can all be deployed in the form of containers. So we need the software that can run containers, and that's the container runtime engine, a popular one being Docker. So we need Docker or its supported equivalent installed on all the nodes in the cluster, including the master nodes, if you wish to host the control plane components as containers. Now, it doesn't always have to be Docker. Kubernetes supports other runtime engines as well, like Containerd or Rocket. Let us now turn our focus onto the cargo ships. Now, every ship has a captain. The captain is responsible for managing all activities on these ships. The captain is responsible for liaising with the master ships, starting with letting the master ship know that they are interested in joining the group, receiving information about the containers to be loaded on the ship, and loading the appropriate containers as required, sending reports back to the master about the status of this ship and the status of the containers on the ship, etc. Now, the captain of the ship is the kubelet in Kubernetes. A kubelet is an agent that runs on each node in a cluster. It listens for instructions from the kube-api server and deploys or destroys containers on the nodes as required. The kube-api server periodically fetches status reports from the kubelet to monitor the status of nodes and containers on them. The kubelet was more of a captain on the ship that manages containers on the ship, but the applications running on the worker nodes need to be able to communicate with each other. For example, you might have a web server running in one container on one of the nodes and a database server running on another container on another node. How would the web server reach the database server on the other node? Communication between worker nodes are enabled by another component that runs on the worker node known as the kube-proxy service. The kube-proxy service ensures that the necessary rules are in place on the worker nodes to allow the containers running on them to reach each other. So, to summarize, we have master and worker nodes. On the master, we have the etcd cluster, which stores information about the cluster. We have the kube-scheduler that is responsible for scheduling applications or containers on nodes. We have different controllers that take care of different functions like the node controller, replication controller, etc. We have the kube-api server that is responsible for orchestrating all operations within the cluster. On the worker node, we have the kubelet that listens for instructions from the kube-api server and manages containers, and the kube-proxy that helps in enabling communication between services within the cluster. So that's a high-level overview of the various components. We will drill down into each of these in the upcoming lectures. That's it for now, and I will see you in the next lecture. Hello and welcome to this lecture. This is a quick introduction to etcd for beginners. If you already know about etcd, feel free to skip this video and head over to the next video where we discuss about etcd in Kubernetes. We start with a basic introduction to what a key value store is and how it is different from traditional databases, how to quickly get started with etcd, and how to use the client tool to operate etcd. Later in this course, when we cover high availability, we will discuss about what it means to be a distributed system, how etcd works in a cluster mode, what Raft protocol is, and what are the best practices around the number of nodes in an etcd cluster. So what is etcd? It is a distributed, reliable key value store that is simple, secure, and fast. So let's break it up. So what is a key value store? Traditionally, databases have been in a tabular format. You must have heard about SQL or relational databases. They store data in the form of rows and columns. For example, here is a table that stores information regarding few individuals. The row represents each person and the column represents the type of information being stored. Now, say we want to add additional details about these individuals. Say, for example, salary. so we add an additional column. Doing so impacts the entire table and all of the individuals in them. We then add salary details to this column. However, not all of them are working, so those cells remain empty. We are then required to store grade information, so we add a new column and update the students with their respective grades. Again, only students have grades, so the corresponding fields for adults are empty. Every time a new information needs to be added, the entire table is affected and leads to a lot of empty cells. A key value store stores information in the form of documents or pages, so each individual gets a document and all information about that individual is stored within that file. These files can be in any format or structure, and changes to one file does not affect the others. The working individuals can have their files with salary fields, and the students can have their pages with grades only. You can add additional details to any of these documents without having to update other similar documents. While you could store and retrieve simple key and values, when your data gets complex, you typically end up transacting in data formats like JSON or YAML. It's easy to install and get started with etcd. Download the binary, extract it, and run. Download the relevant binary for your operating system from the GitHub releases pages, extract it, and run the etcd executable. When you run etcd, it starts a service that listens on port 2379 by default. You can then attach any clients to the etcd service to store and retrieve information. A default client that comes with etcd is the etcd control client. The etcd control client is a command line client for etcd. You can use it to store and retrieve key value pairs. To store a key value pair, run the etcd control set key1 command followed by the value 1. This creates an entry in the database with the information. To retrieve the stored data, run the etcd control get key1 command. To view more options, run the etcd control command without any arguments. Well, that's a quick introduction to etcd. Next, we will see how etcd works in Kubernetes, and later in this course, we will discuss more about configuring etcd clusters in a high availability setup and the best practices around it. Hello and welcome to this lecture. In the previous lecture, we discussed the basics of etcd. In this lecture, we will talk about etcd's role in Kubernetes. The etcd data store stores information regarding the cluster, such as the nodes, pods, configs, secrets, accounts, roles, role bindings, and others. Every information you see when you run the kube-control get command is from the etcd server. Every change you make to your cluster, such as adding additional nodes, deploying pods, or replica sets, are updated in the etcd server. Only once it is updated in the etcd server is the change considered to be complete. Depending on how you set up your cluster, etcd is deployed differently. Throughout this section, we discuss about two types of Kubernetes deployments. One deployed from scratch, and other using the kubeadm tool. The practice test environments are deployed using the kubeadm tool, and later in this course, when we set up a cluster, we set it up from scratch. So it's good to know the difference between the two methods. If you set up your cluster from scratch, then you deploy etcd by downloading the etcd binaries yourself, installing the binaries and configuring etcd as a service in your master node yourself. There are many options passed into the service. A number of them relate to certificates. We will learn more about these certificates, how to create them, and how to configure them later in this course. We have a whole section on TLS certificates. The others are about configuring etcd as a cluster. We will look at those options when we set up high availability in Kubernetes. The only option to note for now is the advertised client URL. This is the address on which etcd listens. It happens to be on the IP of the server and on port 2379, which is the default port on which etcd listens. This is the URL that should be configured on the kube-api server when it tries to reach the etcd server. If you set up your cluster using kubeadm, then kubeadm deploys the etcd server for you as a pod in the kube system namespace. You can explore the etcd database using the etcd control utility within this pod. To list all keys stored by Kubernetes, run the etcd control get command like this. Kubernetes stores data in a specific directory structure. The root directory is a registry, and under that you have the various Kubernetes constructs such as minions or nodes, pods, replica sets, deployments, etc. In a high availability environment, you will have multiple master nodes in your cluster. Then you will have multiple etcd instances spread across the master nodes. In that case, make sure that the etcd instances know about each other by setting the right parameter in the etcd service configuration. The initial cluster option is where you must specify the different instances of the etcd service. We talk about high availability in much more detail later in this course, but I thought it's worthwhile to point it out here. Well, that's it for this lecture, and I will see you in the next. Hello and welcome to this lecture. In this lecture, we will talk about the kube-api server in Kubernetes. Earlier, we discussed that the kube-api server is the primary management component in Kubernetes. When you run a kube-control command, the kube-control utility is in fact reaching to the kube-api server. The kube-api server first authenticates the request and validates it. It then retrieves the data from the etcd cluster and responds back with the requested information. You don't really need to use the kube-control command line. Instead, you could also invoke the APIs directly by sending a post request like this. Let's look at an example of creating a pod. When you do that, as before, the request is authenticated first and then validated. In this case, the API server creates a pod object without assigning it to a node, updates the information in the etcd server, updates the user that the pod has been created. The scheduler continuously monitors the API server and realizes that there is a new pod with no node assigned. The scheduler identifies the right node to place the new pod on and communicates that back to the kube-api server. The API server then updates the information in the etcd cluster. The API server then passes that information to the kubelet in the appropriate worker node. The kubelet then creates the pod on the node and instructs the container runtime engine to deploy the application image. Once done, the kubelet updates the status back to the API server, and the API server then updates the data back in the etcd cluster. A similar pattern is followed every time a change is requested. The kube-api server is at the center of all the different tasks that needs to be performed to make a change in the cluster. To summarize, the kube-api server is responsible for authenticating and validating requests, retrieving and updating data in the etcd data store. In fact, kube-api server is the only component that interacts directly with the etcd data store. The other components such as the scheduler, kube-controller-manager, and kubelet uses the API server to perform updates in the cluster in their respective areas. If you bootstrapped your cluster using kubeadm tool, then you don't need to know this. But if you are setting up the hard way, then the kube-api server is available as a binary in the Kubernetes release page. Download it and configure it to run as a service on your Kubernetes master node. The kube-api server is run with a lot of parameters, as you can see here. Throughout this section, we're going to take a peek at how to install and configure these individual components of the Kubernetes architecture. You don't have to understand all of the options right now, but I think having a high-level understanding on some of these now will make it easier later when we configure the whole cluster and all of its components from scratch. The Kubernetes architecture consists of a lot of different components working with each other, talking to each other in many different ways. So they all need to know where the other components are. There are different modes of authentication, authorization, encryption, and security. And that's why you have so many options. When we go through the relevant section in the course, we will pull up this file and look at the relevant options. For now, we will look at a few important ones. A lot of them are certificates that are used to secure the connectivity between different components. We look at these certificates in more detail when we go through the SSL TLS certificates lecture later in this course. There is a whole section just for it, so we will get rid of them for now. But just remember, all of the various components we are going to look at in this section will have certificates associated with them. The option etcd servers is where you specify the location of the etcd servers. This is how the kube-api server connects to the etcd servers. So how do you view the kube-api server options in an existing cluster? It depends on how you set up your cluster. If you set it up with the kubeadmin tool, the kubeadmin deploys the kube-api server as a pod in the kube system namespace on the master node. You can see the options within the pod definition file located at etc kubernetes manifest folder. In a non-kubeadmin setup, you can inspect the options by viewing the kube-api server service located at etc systemd system kube-api server.service. You can also see the running process and the effective options by listing the process on the master node and searching for kube-api server. Well, that's it for this lecture. Hello and welcome to this lecture. In this lecture, we will talk about kube-controller-manager. As we discussed earlier, the kube-controller-manager manages various controllers in Kubernetes. A controller is like an office or department within the master ship that have their own set of responsibilities. Such as an office for the ships would be responsible for monitoring and taking necessary actions about the ships whenever a new ship arrives or when a ship leaves or gets destroyed. Another office could be one that manages the containers on the ships. They take care of containers that are damaged or fall off ships. So these offices are, number one, continuously on the lookout for the status of the ships, and two, takes necessary actions to remediate the situation. In the Kubernetes terms, a controller is a process that continuously monitors the state of various components within the system and works towards bringing the whole system to the desired functioning state. For example, the node controller is responsible for monitoring the status of the nodes and taking necessary actions to keep the applications running. It does that through the kube-api server. The node controller checks the status of the nodes every 5 seconds. That way, the node controller can monitor the health of the nodes. If it stops receiving heartbeat from a node, the node is marked as unreachable. But it waits for 40 seconds before marking it unreachable. After a node is marked unreachable, it gives it 5 minutes to come back up. If it doesn't, it removes the pods assigned to that node and provisions them on the healthy ones if the pods are part of a replica set. The next controller is the replication controller. It is responsible for monitoring the status of replica sets and ensuring that the desired number of pods are available at all times within the set. If a pod dies, it creates another one. Now, those were just 2 examples of controllers. There are many more such controllers available within Kubernetes. Whatever concepts we have seen so far in Kubernetes, such as deployment, services, namespaces, or persistent volumes, and whatever intelligence is built into these constructs, it is implemented through these various controllers. As you can imagine, this is kind of the brain behind a lot of things in Kubernetes. Now, how do you see these controllers and where are they located in your cluster? They're all packaged into a single process known as the Kubernetes Controller-Manager. When you install the Kubernetes Controller-Manager, the different controllers get installed as well. So how do you install and view the Kubernetes Controller-Manager? Download the kube-controller-manager from the Kubernetes release page, extract it, and run it as a service. When you run it, as you can see, there are a list of options provided. This is where you provide additional options to customize your controller. Remember, some of the default settings for node controller we discussed earlier, such as the node monitor period, the grace period, and the eviction timeout, these go in here as options. There is an additional option called controllers that you can use to specify which controllers to enable. By default, all of them are enabled, but you can choose to enable a select few. So in case any of your controllers don't seem to work or exist, this would be a good starting point to look at. So how do you view the kube-controller-manager server options? Again, it depends on how you set up your cluster. If you set it up with the kubeadmin tool, kubeadmin deploys the kube-controller-manager as a pod in the kube system namespace on the master node. You can see the options within the pod definition file located at Kubernetes manifest folder. In a non-kubeadmin setup, you can inspect the options by viewing the kube-controller-manager service located at the services directory. You can also see the running process and the effective options by listing the process on the master node and searching for kube-controller-manager. Well, that's it for this lecture. I will see you in the next. Hello and welcome to this lecture. In this lecture, we will talk about kube-scheduler. Earlier, we discussed that the Kubernetes scheduler is responsible for scheduling pods on nodes. Now, don't let the graphic mislead you. Remember, the scheduler is only responsible for deciding which pod goes on which node. It doesn't actually place the pod on the nodes. That's the job of the kubelet. The kubelet, or the captain on the ship, is who creates the pod on the ships. The scheduler only decides which pod goes where. Let's look at how the scheduler does that in a bit more detail. First of all, why do you need a scheduler? When there are many ships and many containers, you want to make sure that the right container ends up on the right ship. For example, there could be different sizes of ships and containers. You want to make sure the ship has sufficient capacity to accommodate those containers. Different ships may be going to different destinations. You want to make sure your containers are placed on the right ships so they end up in the right destination. In Kubernetes, the scheduler decides which nodes the pods are placed on depending on certain criteria. You may have pods with different resource requirements. You can have nodes in the cluster dedicated to certain applications. So how does the scheduler assign these pods? The scheduler looks at each pod and tries to find the best node for it. For example, let's take one of these pods, the big blue one. It has a set of CPU and memory requirements. The scheduler goes through two phases to identify the best node for the pod. In the first phase, the scheduler tries to filter out the nodes that do not fit the profile for this pod. For example, the nodes that do not have sufficient CPU and memory resources requested by the pod. So the first two small nodes are filtered out. So we are now left with the two nodes on which the pod can be placed. Now, how does the scheduler pick one from the two? The scheduler ranks the nodes to identify the best fit for the pod. It uses a priority function to assign a score to the nodes on a scale of 0 to 10. For example, the scheduler calculates the amount of resources that would be free on the nodes after placing the pod on them. In this case, the one on the right would have 6 CPUs free if the pod was placed on it, which is 4 more than the other one. So it gets a better rank, and so it wins. So that's how a scheduler works at a high level. And of course, these can be customized and you can write your own scheduler as well. There are many more topics to look at, such as resource requirements, limits, taints and tolerations, node selectors, affinity rules, etc., which is why we have an entire section dedicated to scheduling coming up in this course, where we will discuss each of these in much more detail. For now, we will continue to focus on the scheduler as a process at a high level. So how do you install the kube-scheduler? Download the kube-scheduler binary from the Kubernetes release page, extract it, and run it as a service. When you run it as a service, you specify the scheduler configuration file. So how do you view the kube-scheduler server options? Again, if you set it up with the kubeadm tool, the kubeadm tool deploys the kube-scheduler as a pod in the kube system namespace on the master node. You can see the options within the pod definition file located at Kubernetes manifest folder. You can also see the running process and the effective options by listing the process on the master node and searching for kube-scheduler. Well, that's it for this lecture. I will see you in the next. Or doing all the paperwork necessary to become part of the cluster. They're the sole point of contact from the master ship. They load or unload containers on the ship as instructed by the scheduler on the master. They also send back reports at regular intervals on the status of the ship and the containers on them. The kubelet in the Kubernetes worker node registers the node with a Kubernetes cluster. When it receives instructions to load a container or a pod on the node, it requests the container runtime engine, which may be Docker, to pull the required image and run an instance. The kubelet then continues to monitor the state of the pod and containers in it and reports to the kube-api server on a timely basis. So how do you install the kubelet? If you use the kubeadm tool to deploy your cluster, it does not automatically deploy the kubelet. Now that's the difference from the other components. You must always manually install the kubelet on your worker nodes. Download the installer, extract it, and run it as a service. You can view the running kubelet process and the effective options by listing the process on the worker node and searching for kubelet. We will look more into kubelets, how to configure kubelets, generate certificates, and finally how to TLS bootstrap kubelets later in this course. That's it for now. I will see you in the next lecture. Hello and welcome to this lecture. In this lecture, we will talk about kube-proxy. Within a Kubernetes cluster, every pod can reach every other pod. This is accomplished by deploying a pod networking solution to the cluster. A pod network is an internal virtual network that spans across all the nodes in the cluster to which all the pods connect to. Through this network, they're able to communicate with each other. There are many solutions available for deploying such a network. In this case, I have a web application deployed on the first node and a database application deployed on the second. The web app can reach the database simply by using the IP of the pod. But there is no guarantee that the IP of the database pod will always remain the same. If you have gone through the lecture on services, as discussed in the beginner's course, you must know that a better way for the web application to access the database is using a service. So we create a service to expose the database application across the cluster. The web application can now access the database using the name of the service, DB. The service also gets an IP address assigned to it. Whenever a pod tries to reach the service using its IP or name, it forwards the traffic to the backend pod, in this case, the database. But what is this service and how does it get an IP? Does the service join the same pod network? The service cannot join the pod network because the service is not an actual thing. It is not a container like pods, so it doesn't have any interfaces or an actively listening process. It is a virtual component that only lives in the Kubernetes memory. But then we also said that the service should be accessible across the cluster from any nodes. So how is that achieved? That's where kube-proxy comes in. Kube-proxy is a process that runs on each node in the Kubernetes cluster. Its job is to look for new services, and every time a new service is created, it creates the appropriate rules on each node to forward traffic to those services to the backend pods. One way it does this is using IP tables rules. In this case, it creates an IP tables rule on each node in the cluster to forward traffic heading to the IP of the service, which is 10.96.0.12, to the IP of the actual pod, which is 10.32.0.15. So that's how kube-proxy configures a service. We discuss a lot more about networking and services and kube-proxy and pod networking later in this course. Again, we have a large section just for networking. This is a high-level overview for now. We will now see how to install kube-proxy. Download the kube-proxy binary from the Kubernetes release page, extract it, and run it as a service. The kubeadm tool deploys kube-proxy as pods on each node. In fact, it is deployed as a daemon set, so a single pod is always deployed on each node in the cluster. Well, if you don't know about daemon set yet, don't worry. We have a lecture on that coming up in this course. We have now covered a high-level overview of the various components in the Kubernetes control plane. As mentioned, we will look at some of these in much more detail at various sections in this course. Well, that's it for this lecture. I will see you in the next section. Hello and welcome to this lecture on Kubernetes pods. Before we head into understanding pods, we would like to assume that the following have been set up already. At this point, we assume that the application is already developed and built into Docker images, and it is available on a Docker repository like Docker Hub, so Kubernetes can pull it down. We also assume that the Kubernetes cluster has already been set up and is working. This could be a single node setup or a multi-node setup, doesn't matter. All the services need to be in a running state. As we discussed before, with Kubernetes, our ultimate aim is to deploy our application in the form of containers on a set of machines that are configured as worker nodes in a cluster. However, Kubernetes does not deploy containers directly on the worker nodes. The containers are encapsulated into a Kubernetes object known as pods. A pod is a single instance of an application. A pod is the smallest object that you can create in Kubernetes. Here we see the simplest of simplest cases where you have a single node Kubernetes cluster with a single instance of your application running in a single Docker container encapsulated in a pod. What if the number of users accessing your application increase and you need to scale your application? You need to add additional instances of your web application to share the load. Now, where would you spin up additional instances? Do we bring up new container instance within the same pod? No. We create new pod altogether with a new instance of the same application. As you can see, we now have two instances of our web application running on two separate pods on the same Kubernetes system or node. What if the user base further increases and your current node has no sufficient capacity? Well, then you can always deploy additional pods on a new node in the cluster. You will have a new node added to the cluster to expand the cluster's physical capacity. So what I'm trying to illustrate in this slide is that pods usually have a one-to-one relationship with containers running your application. To scale up, you create new pods, and to scale down, you delete existing pods. You do not add additional containers to an existing pod to scale your application. Also, if you're wondering how we implement all of this and how we achieve load balancing between the containers, etc., we will get into all of that in a later lecture. For now, we are only trying to understand the basic concepts. We just said that pods usually have a one-to-one relationship with the containers. But are we restricted to having a single container in a single pod? No. A single pod can have multiple containers except for the fact that they're usually not multiple containers of the same kind. As we discussed in the previous slide, if our intention was to scale our application, then we would need to create additional pods. But sometimes you might have a scenario where you have a helper container that might be doing some kind of supporting task for our web application, such as processing a user-entered data, processing a file uploaded by the user, etc. And you want these helper containers to live alongside your application container. In that case, you can have both of these containers part of the same pod, so that when a new application container is created, the helper is also created, and when it dies, the helper also dies since they are part of the same pod. The two containers can also communicate with each other directly by referring to each other as localhost, since they share the same network space. Plus, they can easily share the same storage space as well. If you still have doubts in this topic, I would understand if you did, because I did the first time I learned these concepts, we could take another shot at understanding pods from a different angle. Let's, for a moment, keep Kubernetes out of our discussion and talk about simple Docker containers. Let's assume we were developing a process or a script to deploy our application on a Docker host. Then we would first simply deploy our application using a simple docker run Python app command, and the application runs fine and our users are able to access it. When the load increases, we deploy more instances of our application by running the docker run commands many more times. This works fine and we're all happy. Now, sometime in the future, our application is further developed, undergoes architectural changes, and grows and gets complex. We now have a new helper container that helps our web application by processing or fetching data from elsewhere. These helper containers maintain a one-to-one relationship with our application container and thus needs to communicate with the application containers directly and access data from those containers. For this, we need to maintain a map of what app and helper containers are connected to each other. We would need to establish network connectivity between these containers ourselves using links and custom networks. We would need to create shareable volumes and share it among the containers. We would need to maintain a map of that as well. And most importantly, we would need to monitor the state of the application container, and when it dies, manually kill the helper container as well, as it's no longer required. When a new container is deployed, we would need to deploy the new helper container as well. With pods, Kubernetes does all of this for us automatically. We just need to define what containers a pod consists of, and the containers in a pod by default will have access to the same storage, the same network namespace, and same fate, as in they will be created together and destroyed together. Even if our application didn't happen to be so complex and we could live with a single container, Kubernetes still requires you to create pods. But this is good in the long run, as your application is now equipped for architectural changes and scale in the future. However, also note that multi-pod containers are a rare use case, and we're going to stick to single containers per pod in this course. Let us now look at how to deploy pods. Earlier, we learned about the kubectl run command. What this command really does is, it deploys a Docker container by creating a pod. So it first creates a pod automatically and deploys an instance of the nginx Docker image. But where does it get the application image from? For that, you need to specify the image name using the --image parameter. The application image, in this case the nginx image, is downloaded from the Docker Hub repository. Docker Hub, as we discussed, is a public repository where latest Docker images of various applications are stored. You could configure Kubernetes to pull the image from the public Docker Hub or a private repository within the organization. Now that we have a pod created, how do we see the list of pods available? The kube-control get pods command helps us see the list of pods in our cluster. In this case, we see the pod is in a container creating state and soon changes to a running state when it is actually running. Also remember that we haven't really talked about the concepts on how a user can access the nginx web server. And so in the current state, we haven't made the web server accessible to external users. You can, however, access it internally from the node. For now, we will just see how to deploy a pod, and in a later lecture, once we learn about networking and services, we will get to know how to make this service accessible to end users. That's it for this lecture. Hello and welcome to this lecture. My name is Mumshad Manambeth and we are learning Kubernetes for beginners. In this lecture, we will talk about creating a pod using a YAML-based configuration file. In the previous lecture, we learned about YAML files in general. Now we will learn how to develop YAML files specifically for Kubernetes. Kubernetes uses YAML files as inputs for the creation of objects such as pods, replicas, deployments, services, etc. All of these follow a similar structure. A Kubernetes definition file always contains 4 top-level fields: the API version, kind, metadata, and spec. These are the top-level or root-level properties. These are also required fields, so you must have them in your configuration file. Let us look at each one of them. The first one is the API version. This is the version of the Kubernetes API we are using to create the object. Depending on what we are trying to create, we must use the right API version. For now, since we are working on pods, we will set the API version as v1. Few other possible values for this field are apps/v1 beta, extensions/v1 beta, etc. We will see what these are for later in this course. Next is the kind. The kind refers to the type of object we are trying to create, which in this case happens to be a pod. So we will set it as pod. Some other possible values here could be replica set or deployment or service, which is what you see in the kind field in the table on the right. The next is metadata. The metadata is data about the object, like its name, labels, etc. As you can see, unlike the first two where you have specified a string value, this is in the form of a dictionary. So everything under metadata is intended to the right a little bit, and so names and labels are children of metadata. The number of spaces before the two properties, name and labels, doesn't matter, but they should be the same as they are siblings. In this case, labels has more spaces on the left than name, and so it is now a child of the name property instead of a sibling, which is incorrect. Also, the two properties must have more spaces than its parent, which is metadata, so that it's intended to the right a little bit. In this case, all 3 of them have the same number of spaces before them, and so they are all siblings, which is not correct. Under metadata, the name is a string value, so you can name your pod my app pod. And the labels is a dictionary, so labels is a dictionary within the metadata dictionary. And it can have any key and value pairs as you wish. For now, I have added a label app with the value my app. Similarly, you could add other labels as you see fit, which will help you identify these objects at a later point in time. Say, for example, there are hundreds of pods running a front-end application and hundreds of pods running a back-end application or a database. It will be difficult for you to group these pods once they are deployed. If you label them now as front-end, back-end, or database, you will be able to filter the pods based on this label at a later point in time. It's important to note that under metadata, you can only specify name or labels or anything else that Kubernetes expects to be under metadata. You cannot add any other property as you wish under this. However, under labels, you can have any kind of key or value pairs as you see fit. So it's important to understand what each of these parameters expect. So far, we have only mentioned the type and name of the object we need to create, which happens to be a pod with the name myAppPod. But we haven't really specified the container or image we need in the pod. The last section in the configuration file is the specification section, which is written as spec. Depending on the object we are going to create, this is where we would provide additional information to Kubernetes pertaining to that object. This is going to be different for different objects, so it's important to understand or refer to the documentation section to get the right format for each. Since we are only creating a pod with a single container in it, it is easy. Spec is a dictionary, so add a property under it called containers. Containers is a list or an array. The reason this property is a list is because the pods can have multiple containers within them, as we learned in the lecture earlier. In this case though, we will only add a single item in the list, since we plan to have only a single container in the pod. The dash right before the name indicates that this is the first item in the list. The item in the list is a dictionary, so add a name and image property. The value for image is nginx, which is the name of the Docker image in the Docker repository. Once the file is created, run the command kubectl create -f followed by the file name, which is pod definition.yaml, and Kubernetes creates the pod. So to summarize, remember the 4 top-level properties: API version, kind, metadata, and spec. Then start by adding values to those depending on the object you are going to create. Once we create the pod, how do you see it? Use the kubectl getPods command to see a list of pods available. In this case, it's just one. To see detailed information about the pod, run the kubectl describe pod command. This will tell you information about the pod, when it was created, what labels are assigned to it, what Docker containers are part of it, and the events associated with that pod. That's it for this lecture. We will now head over to a demo, and I will see you in the next lecture. Hello and welcome to this demo. In this demo, we're going to see how to create a pod using a YAML definition file. Okay, so in order to create YAML files, you can actually use any editor of your choice. You could even use just a Notepad or Notepad++ or Atom, or there are multiple options available. In my case, I tend to use PyCharm or a tool from the JetBrains family. So I personally use PyCharm, which is actually a Python editor, and it has good support for YAML files. So I use JetBrains PyCharm as my editor. If you'd like to use PyCharm, you can actually go to jetbrains.com and select PyCharm, jetbrains.com/PyCharm, and you can actually see when you click on download, you can actually see there are 2 options. One is a professional version and another is community version, which is free. So you can actually download this lightweight IDE, which is free to develop definition files. And later on, I will also show some tips and tricks around using this IDE, which will make your life developing Kubernetes definition files in YAML very easy. So there are ways that there are plugins that will help you validate your file available with PyCharm. So we'll look at those as well. So to start with, I'm going to create a new project. I'm going to call it as pod, and I'm just going to create the project. So that's my folder named pod, and under pod, I'm going to start by creating a pod definition file. I'm going to name that pod-definition.yaml. And so now I have one file, and as we saw in the lecture, every Kubernetes definition file has the 4 root level properties, which are API version. So I'm going to specify each of those. So we have API version, kind, metadata, and spec. Okay, so as we discussed, API version is going to be v1 for pod. The kind, as we know, is pod, so I'm going to set that as pod. The metadata is an object or a dictionary, so I'm going to hit enter, and then I'm going to hit tab, or you can actually use spaces as well. I'm going to provide the properties under metadata, which are name, and I'm going to set a name for my pod, which is going to be my app-pod. And when I hit enter, as you see, it goes to the next line, but it's indented
it has equal number of spaces before it than the previous line. And I'm going to have labels and under labels. So since labels is a dictionary again, I'm going to indent the next few lines to the right as well. Under labels, I have app, and the name of the app is going to be my app. Now, if you look at this whole file, and if you look at the bottom, PyCharm has support for understanding YAML files. So if you look at the bottom, you can actually see the various elements in a tree structure. So as you can see, document 1 of 1 indicates this file, the entire file. And under this file, it actually shows you in tree structure the various properties. So you have API version, which is directly under the file. Kind, metadata, and spec are all directly under the file or root properties of the file, which is what we wanted. And if you look at V1 is actually under API version. So now, as you can see, under the document, I have API version, and under that, I have V1. So that matches what we're trying to do. Similarly, if I select pod, you can see that it's under kind. And if you select name, which is under metadata, you can see that it's under metadata. Similarly, when you select labels, you will also see that it is under metadata. So that means name and labels are children of metadata, and they are siblings, and they must be intended. They must have the same indentation. So under a name, you have my app pod, so you can see the hierarchy there. Similarly, app is under labels, and my app is under app, which is under labels. Now, if you look at it, name and labels need to be on the same vertical line. For now, if I simply move labels to the right, you will now see that labels is under name. So labels is now a child of name, which is not right. It is supposed to be a sibling. So I'm going to remove those extra spaces. I'm going to hit backspace, and I'm going to level it. So this is right. And under labels, you can actually have as many labels as you want. So you can create any key value pair here. You can say cost center is Amer, location North America, or something like the type of this particular pod, maybe a front end or something like that. So anything that will help you group this particular pod in the future. For now, I'm just going to remove all of that, and I'll now move on to the specs section. Under the specs section, remember the specs section is unique to each object that you're creating. So for a pod, under the specs section, you actually have containers, and under containers, you have the containers is in fact an array, or a list. So you have a list of items. So you need each item in the list is identified by a dash. So you have to put a dash followed by a space, and then name, which is the name of my pod. The name of my container inside the pod, and that's going to be INX control container. And then I have image, which is the name of the image itself, which is INX. So if you look at it, I have under spec, I have containers, which is a list, and then I have an item in the list, which has name and image. Now, if we try and look at the hierarchy of what we just created, say if I select name, I see that it's under spec and it's under containers, but there's something in between which says item 1 of 1. What that actually means is that's what indicates that the container is a list and it has multiple items, and this is the first item of just one item. So this 2 lines is 1 item in the containers. Similarly, you can have, we know that we discussed that you can have additional containers in a pod. So if you had additional containers, then this is how you would define it. You would, in the new line, you would add a new dash followed by new information about followed by information about the new pod, which could be like a backend container, and the image is could be something like Redis or something. So in this case, now when I select name, you can actually see that it says item 2 of 2 and then 1 of 2. So now it actually identifies each item in the array or the list. So that indicates that our format is correct, and that is what we were trying to do. I'm just going to get rid of the second container. Then I'm going to leave it as one container per pod. So this is good. I'm now going to copy the contents of this, and create an actual pod using this the content that we just created. So I'm going to go to the Kube master. I'm going to create a folder structure for my demos. So I'm going to call it demos, and under demos I'm going to create a folder called pod, and under pod I'm going to create a file named pod definition.yaml, and I will paste the contents that I just created. Okay, so when I now I'm going to verify the contents of the file. I can now run the kube-control get pods command. Before I create the pod, I just want to make sure there's nothing running. So if you're following me from the previous lab where I deployed a pod using the kube-control run command, that's the pod that's still running. So I'm going to get rid of that using the kube-control delete deployment command. So that's gone. When I now run the kube-control get pods command, I see that there are no resources found. I can now create a new pod using the kube-control create pod definition.yaml command, and I see that a new pod, my app pod, is created. When I run the kube-control get pods command, I see that it's in the process of creating the container, and I will now monitor it, and when I run it again, I see that it's in a running state. Well, that's it for this lecture. In the next demo, we're going to look at some tips and tricks around working with YAML files in PyCharm. Thank you for your time, and I will see you in the next demo.
On more of these and improving and making these more challenging and fun. I hope you like it. I hope it helps you gain practice. If you come across any issues, please do report it to me, and please bear with me until I fix it. Thank you once again for your support and cooperation, and I wish you good luck in the upcoming practice tests. Hello. In this video, I will explain how to access labs part of this course. This course comes with real hands-on labs that you can access right in your browser. Unfortunately, Udemy does not have native support for embedding real hands-on labs in the course, and that's why these labs are hosted on CodeCloud. Students who purchase this course on Udemy can get access to the labs for free on CodeCloud. You don't have to make any extra payments. To access the labs, there is a lecture named Access Labs in your course. It is under the Core Concepts section in the course for CKA and CKAD, right before the first lab starts. In the lecture, there is a link with a coupon code to enroll in the labs. Clicking on the link will take you to CodeCloud. CodeCloud and Udemy are different platforms, and unfortunately, there is no option available yet to share the same user accounts between the two. So you must create an account and sign up on CodeCloud to access the labs. Remember, your Udemy credentials won't work on CodeCloud. If you're accessing through Udemy for Business, then your company credentials won't work either. You must create a new account on CodeCloud. This is something we hope to improve in the future. If for some reason the coupon code is not applied and shows you a charge, then just apply the coupon code manually. Note that the coupon code may not be the same as what you see in this video, so remember to use the correct one from the lecture when you access the labs. Once you're done, you should see the labs under the My Courses section on CodeCloud. After each lecture in Udemy, we have a link that will take you directly to the lab you need to do in CodeCloud. As long as you're enrolled in the labs on CodeCloud and you're logged in, you should be good. Finally, you might get a notification email that looks like this, with a charge on it. This is an auto-generated email, and for some reason, it does not take into account the free coupon applied. It shows the original price of the labs. So that's why you see this charge here. So you can simply ignore the amount shown there. You're not charged any extra amount for these labs. And one more thing before you go. If for some reason you see this message when you try to access a lab, then it means two things. One, you have not enrolled in the labs using the links shared in the course. Remember, each course has a different labs. CKA and CKAD courses have different labs and different links that you should be using to enroll. If you have already enrolled, then chances are that you're not logged in, you're probably logged out. So you can then log in again to CodeCloud and try accessing the labs again. Well, that's it for now. If you follow these instructions and you're still having trouble accessing the labs, please shoot us an email at support@codecloud.com. Thank you very much, and I hope you enjoy the labs. Hello. Before you head into a practice test, which follows this video, I wanted to spend a few minutes on walking you through Hello and welcome to this lecture on Kubernetes controllers. My name is Mumshad Manambeth. In this lecture, we will discuss about Kubernetes controllers. Controllers are the brain behind Kubernetes. They are the processes that monitor Kubernetes objects and respond accordingly. In this lecture, we will discuss about one controller in particular, and that is the replication controller. So, what is a replica and why do we need a replication controller? Let's go back to our first scenario where we had a single pod running our application. What if for some reason our application crashes and the pod fails? Users will no longer be able to access our application.
To prevent users from losing access to our application, we would like to have more than one instance or pod running at the same time. That way, if one fails, we still have our application running on the other one. The replication controller helps us run multiple instances of a single pod in the Kubernetes cluster, thus providing high availability. So does that mean you can't use a replication controller if you plan to have a single pod? No. Even if you have a single pod, the replication controller can help by automatically bringing up a new pod when the existing one fails. Thus, the replication controller ensures that the specified number of pods are running at all times, even if it's just 1 or 100. Another reason we need replication controller is to create multiple pods to share the load across them. For example, in this simple scenario, we have a single pod serving a set of users. When the number of users increase, we deploy additional pod to balance the load across the two pods. If the demand further increases, and if we were to run out of resources on the first node, we could deploy additional pods across the other nodes in the cluster. As you can see, the replication controller spans across multiple nodes in the cluster. It helps us balance the load across multiple pods on different nodes as well as scale our application when the demand increases. It's important to note that there are two similar terms, replication controller and replica set. Both have the same purpose, but they're not the same. Replication controller is the older technology that is being replaced by replica set. Replica set is the new recommended way to set up replication. However, whatever we discussed in the previous few slides remain applicable to both these technologies. There are minor differences in the way each works, and we will look at that in a bit. As such, we will try to stick to replica sets in all of our demos and implementations going forward. Let us now look at how we create a replication controller. As with the previous lecture, we start by creating a replication controller definition file. We will name it rc-definition.yaml. As with any Kubernetes definition file, we have 4 sections: the API version, kind, metadata, and spec. The API version is specific to what we are creating. In this case, replication controller is supported in Kubernetes API version v1. So we will set it as v1. The kind, as we know, is replication controller. Under metadata, we will add a name and we will call it myapp-rc, and we will also add a few labels, app and type, and assign values to them. So far, it has been very similar to how we created a pod in the previous section. The next is the most crucial part of the definition file, and that is the specification written as spec. For any Kubernetes definition file, the spec section defines what's inside the object we are creating. In this case, we note that the replication controller creates multiple instances of a pod. But what pod? We create a template section under spec to provide a pod template to be used by the replication controller to create replicas. Now, how do we define the pod template? It's not that hard because we have already done that in the previous exercise. Remember, we created a pod definition file in the previous exercise. We could reuse the contents of the file to populate the template section. Move all the contents of the pod definition file into the template section of the replication controller, except for the first few lines, which are API version and kind. Remember, whatever we move must be under the template section, meaning they should be intended to the right and have more spaces before them than the template line itself. They should be children of the template section. Looking at our file now, we now have 2 metadata sections. One is for the replication controller and another for the pod, and we have two spec sections, one for each. We have nested two definition files together, the replication controller being the parent and the pod definition being the child. Now there is something still missing. We haven't mentioned how many replicas we need in the replication controller. For that, add another property to the spec called replicas and input the number of replicas you need under it. Remember that the template and replicas are direct children of spec sections, so they are siblings and must be on the same vertical line, which means having equal number of spaces before them. Once the file is ready, run the kubectl create command and input the file using the -f parameter. The replication controller is created. When the replication controller is created, it first creates the pods using the pod definition template, as many as required, which is 3 in this case. To view the list of created replication controllers, run the kubectl get replication controller command and you will see the replication controller listed. We can also see the desired number of replicas or pods, the current number of replicas, and how many of them are ready in the output. If you would like to see the pods that were created by the replication controller, run the kubectl get pods command and you will see 3 pods running. Note that all of them are starting with the name of the replication controller, which is myapp-rc, indicating that they are all created automatically by the replication controller. What we just saw was the replication controller. Let us now look at replica set. It is very similar to replication controller. As usual, first we have API version, kind, metadata, and spec. The API version, though, is a bit different. It is apps/v1, which is different from what we had before for replication controller, which was just v1. If you get this wrong, you are likely to get an error that looks like this. It would say no match for kind replica set, because the specified Kubernetes API version has no support for replica set. The kind would be replica set, and we add name and labels in the metadata. The specification section looks very similar to replication controller. It has a template section where we provide pod definition as before. So I'm going to copy contents over from pod definition file, and we have number of replicas, which is set to 3. However, there is one major difference between replication controller and replica set. Replica set requires a selector definition. The selector section helps the replica set identify what pods fall under it. But why would you have to specify what pods fall under it if you have provided the contents of the pod definition file itself in the template? It's because replica set can also manage pods that were not created as part of the replica set creation. Say, for example, there were pods created before the creation of the replica set that match labels specified in the selector. The replica set will also take those pods into consideration when creating the replicas. I will elaborate this in the next slide. But before we get into that, I would like to mention that the selector is one of the major differences between replication controller and replica set. The selector is not a required field in case of a replication controller, but it is still available. When you skip it, as we did in the previous slide, it assumes it to be the same as the labels provided in the pod definition file. In case of replica set, a user input is required for this property, and it has to be written in the form of match labels as shown here. The match labels selector simply matches the labels specified under it to the labels on the pod. The replica set selector also provides many other options for matching labels that were not available in a replication controller. And as always, to create a replica set, run the kubectl create command providing the definition file as input. And to see the created replicas, run the kubectl get replica set command. To get list of pods, simply run the kube-control-getPods command. So what is the deal with labels and selectors? Why do we label our pods and objects in Kubernetes? Let us look at a simple scenario. Say we deployed 3 instances of our front-end web application as 3 pods. We would like to create a replication controller or replica set to ensure that we have 3 active pods at any time. And yes, that is one of the use cases of replica sets. You can use it to monitor existing pods if you have them already created, as it is in this example. In case they were not created, the replica set will create them for you. The role of the replica set is to monitor the pods and if any of them were to fail, deploy new ones. The replica set is in fact a process that monitors the pods. Now, how does the replica set know what pods to monitor? There could be hundreds of other pods in the cluster running different applications. This is where labeling our pods during creation comes in handy. We could now provide these labels as a filter for replica set. Under the selector section, we use the match labels filter and provide the same label that we used while creating the pods. This way, the replica set knows which pods to monitor. The same concept of labels and selectors is used in many other places throughout Kubernetes. Now, let me ask you a question along the same lines. In the replica set specification section, we learned that there are 3 sections: template, replicas, and the selector. We need 3 replicas, and we have updated our selector based on our discussion in the previous slide. Say, for instance, we have the same scenario as in the previous slide, where we have 3 existing pods that were created already, and we need to create a replica set to monitor the pods to ensure there are a minimum of 3 running at all times. When the replication controller is created, it is not going to deploy a new instance of pod as 3 of them with matching labels are already created. In that case, do we really need to provide a template section in the replica set specification, since we are not expecting the replica set to create a new pod on deployment? Yes, we do, because in case one of the pods were to fail in the future, the replica set needs to create a new one to maintain the desired number of pods. And for the replica set to create a new pod, the template definition section is required. Let's now look at how we scale the replica set. Say we started with 3 replicas, and in the future we decided to scale to 6. How do we update our replica set to scale to 6 replicas? Well, there are multiple ways to do it. The first is to update the number of replicas in the definition file to 6. Then, run the kubectl replace command to specify the same file using the -f parameter, and that will update the replica set to have 6 replicas. The second way to do it is to run the kube-control-scale command, use the replicas parameter to provide the new number of replicas and specify the same file as input. You may either input the definition file or provide the replica set name in the type name format. However, remember that using the file name as input will not result in the number of replicas being updated automatically in the file. In other words, the number of replicas in the replica set definition file will still be 3, even though you scaled your replica set to have 6 replicas using the kube-control-scale command and the file as input. There are also options available for automatically scaling the replica set based on load, but that is an advanced topic and we will discuss it at a later time. Let us now review the commands real quick. The kube-control-create command, as we know, is used to create a replica set, or basically any object in Kubernetes, depending on the file we are providing as input. You must provide the input file using the -f parameter. Use the kube-control-get command to see list of replica sets created. Use the kube-control-delete replica set command followed by the name of the replica set to delete the replica set. And then we have the kube-control-replace command to replace or update the replica set, and also the kube-control-scale command to scale replica set simply from the command line without having to modify the file. That's it for this lecture. Hello and welcome to this lecture. My name is Momshad Manambet. In this lecture, we will discuss about Kubernetes deployments. For a minute, let us forget about pods and replica sets and other Kubernetes concepts and talk about how you might want to deploy your application in a production environment. Say, for example, you have a web server that needs to be deployed in a production environment. You need not one, but many such instances of the web server running for obvious reasons. Secondly, whenever newer versions of application builds become available on the Docker registry, you would like to upgrade your Docker instances seamlessly. However, when you upgrade your instances, you do not want to upgrade all of them at once as we just did. This may impact users accessing our application, so you might want to upgrade them one after the other. And that kind of upgrade is known as rolling updates. Suppose one of the upgrades you performed resulted in an unexpected error and you're asked to undo the recent change. You would like to be able to roll back the changes that were recently carried out. Finally, say for example, you would like to make multiple changes to your environment, such as upgrading the underlying web server versions, as well as scaling your environment and also modifying the resource allocations, etc. You do not want to apply each change immediately after the command is run. Instead, you would like to apply a pause to your environment, make the changes, and then resume so that all the changes are rolled out together. All of these capabilities are available with the Kubernetes deployments. So far in this course, we discussed about pods, which deploy single instances of our application, such as the web application in this case. Each container is encapsulated in pods. Multiple such pods are deployed using replication controllers or replica sets. And then comes deployment, which is a Kubernetes object that comes higher in the hierarchy. The deployment provides us with the capability to upgrade the underlying instances seamlessly using rolling updates, undo changes, and pause and resume changes as required. So how do we create a deployment? As with the previous components, we first create a deployment definition file. The contents of the deployment definition file are exactly similar to the replica set definition file, except for the kind, which is now going to be deployment. If we walk through the contents of the file, it has an API version, which is apps/v1,
metadata, which has name and labels, and a spec that has template, replicas, and selector. The template has a pod definition inside it. Once the file is ready, run the kube-control create command and specify to see the newly created deployment. The deployment automatically creates a replica set. So if you run the kube-control get replica set command, you will be able to see a new replica set in the name of the deployment. The replica sets ultimately create pods. So if you run the kube-control get pods command, you will be able to see the pods with the name of the deployment and the replica set. So far, there hasn't been much of a difference between replica set and deployments, except for the fact that deployment created a new Kubernetes object called deployments. We will see how to take advantage of the deployment using the use cases we discussed in the previous slide in the upcoming lectures. And one more note before we end this lecture: to see all the created objects at once, run the kube-control get all command. And in this case, we can see that the deployment was created, and then we have the replica set, followed by 3 pods that were created as part of the deployment. That's it for this lecture. Hello, and welcome to this